are liars, you just think your globe's so pretty. I'm 100 miles away, but I still clearly see that city. How about you? Does math explain this? I want proof, not some old goof. FE deniers, don't you worry about the distance. I can see you there across the lake while laser pointers glisten. Use your eyes. Just hear my words, see through the lies.
Hello, and welcome to Ether Cosmology Reading Night number 18. We've done 18 of these now, official reading nights. That's not including the 3 Brenner Comp reading nights and all the other random times that we pull papers up and read them. But since we started doing these official reading nights, we've done it for 18 weeks straight now, so that's pretty fun. And for the last, 3, 4 weeks, we've been reading from Shankar's physics book, Fundamentals of Physics 1. But today we're taking a break from that. And we're going to read about redshift, and we're read Halton Arp's Seeing Red, and we're going to read the section about gravitational lenses, which also discusses the Einstein cross, which was particularly what caught my attention when I was flipping through the book earlier today. And so, yeah, I'll throw the quick little disclaimer on there for these nights. We literally read on these nights. Sometimes we do some live research and we'll pause the reading to look things up and ask questions and stuff, but the purpose of this is not to necessarily make things super entertaining or to, do a presentation for you, but rather for you to get in some insight into our research process and our reading process. So there you go. So I guess who wants to get started?
I'll lead us in
I suppose.
with
All right, go ahead.
gravitational lensing. All right. So this is Halton Arp's book Seeing Red. So we're on chapter 7, gravitational lenses. Prior to the 1950s, Fritz Zwicky, the Swiss astronomer who had an illustrious and turbulent career in California, was aware that the strong gravitational fields had been shown to bend light rays, as in the famous eclipse observations of displacement of positions of stars observed at the grazing angles of the sun's limb. At the time, he had started looking for extragalactic objects, which might have been directly behind another, and thus having the outer light rays bend inward in the inward by the gravitational field in the foreground object, so that it formed into a rim or a halo. Some ring galaxies were found, but it all seemed to be physical rings around the galaxy and not magnified by background objects. The more common situation to be expected was when the background object was not exactly centered and the gravitational ring collapsed into a sided arc. But no striking example of that were found either. So some objects had gone dormant.
Thanks, robot here. What else? That problem?
Oh yeah. Oh yeah.
Yeah, it's robot.
Dang. Okay.
Oh yeah.
That's
It's
gonna cause a
So are
massive
you a little
problem.
bit there.
yeah, it's definitely gonna robot all night. Discord's lagging hard.
We either need to change platforms or cancel.
We can hop on Telegram.
We could try it on Telegram. Let's see here. I'll pull that up. All right, I'll do it. I'll hop over to Ether Cosmology on Telegram. How does this even work? I remember it being really weird to find.
Can you post a link when you do?
Yeah, of course. How to start voice call. Here we go. Start video chat. Okay. Ether cosmology. Continue. All right. All right. Let's see. Mute. I'm gonna mute and deafen here and tell them to start for a second while I test. Testing, testing. You hear me, Alan?
Yep, real good.
Yep. Sounds good.
Yeah, you sound good too. Okay, cool.
Cool.
Now let's see if we can share screen.
We definitely
Cool.
can.
Nice, 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 nice. Did you want to keep sharing then?
Yep.
Cool. Okay. Well, this looks like this will work. Let me drop a link in the chat for everybody.
Yep.
Sweet.
You will have to mute your mic when you're not talking though. There's a little, we can hear your fan.
You're a little clicky sounding, but it's at least not roboting like it was. So everyone that's listening in, thanks for bearing with us here. We just, as you can see, Discord is acting up tonight, so we're having a little bit of technical problems.
Let me send Stone the link here.
Cool, you got that? Cool.
Yeah, we gotta invite everyone from Discord to come on over to Telegram, no?
Yep.
Man, it's like I'm getting like a clickiness from you guys.
It sounds good for me. Although I heard
Wonder
that
if
click just
maybe-
now. What was that? Is that Bill Gates clicking? Is he in there clicking?
Yeah, maybe. I don't know. I don't. It's happening for me too, though.
See if that's any better for me.
Do you hear it, Shane? Like the clicky sound in the
Yeah.
background?
Yeah. But I did just
Yeah.
turn on noise suppression and change default mic to this, so it should be better.
Oh, you know what? That's a good call. Let me make sure mine's all set up as well.
I mean, yeah, it's pretty rough, honestly.
All right. How does it
For
sound?
reading.
Does it still sound okay?
Echoey?
Yeah, I think so.
Really? I turned on noise suppression.
Oh,
I think
no,
it's good.
Okay. Cool.
Man, there's something weird, like a software thing going on though. It's like just a little bit.
Look.
Honestly, it sounds good now. Just ignore the sniffing sounds and let's roll.
Cool.
Yo, Toby, can you mute your mic real quick? Ah, there you go. Yeah. Gotta keep it muted when you're not talking.
My bad. I honestly didn't realize that was unmuted.
Oh, you're good.
We're just waiting for Stone.
I sent them the link, so but I'm good to whenever you guys are good.
Sure.
Cool. All right. The sudden revival of gravitational lensing to the huge industry in it is today is simply due to quasars. So the revival of gravitational lensing is due to quasars today, the interest in it. In the 1960s and 1970s, I started finding high densities of quasars concentrated around nearby low redshift galaxies. Because of their high redshifts, it was felt that they could not be associated with the low redshift galaxy. As described in Quasars, Redshift, and Controversies, the observations were simply rejected as being incorrect. Then a theoretician named Claude Cannerzers got the idea that these apparent associations might be background quasars magnified in brightness by gravitational lensing effects of the foreground galaxy. Suddenly, the observations were hailed. Dude, no way. They found relativity right where they were looking for it. Suddenly, the observations were hailed as important and correct. And many of the examples of the concentrations of the quasars around the lower redshifts were found, and many more examples. Excess quasars around galaxies. And so what quasars are, by the way, are little tiny dots of huge amounts of energy in the sky where based off of how their noble ladder, which is how they interpret distances. So based off of the magnitude of brightnesses and energy outputs of everything that they look at in the sky, these have way too much energy output. So they assume that they have to be, they make them like really far. So that's why they don't move. And they tell this story that like, oh, it's just some crazy energy output that's stationary in the sky, essentially. So when they talk about movement, sorry, go ahead.
When I was face deep in textbooks years ago, quasar was spelled out as quasi-stellar object, just to add to the weirdness of what you're talking about there. Go on.
Yeah. So, they analyze this through the spectral shift, right? So that when they split light into a frequency, into a rainbow, and they're looking at it, they're like, oh, no way. It's this amount of red. So this must mean it's so, it's expanding away. This is where they're interpreting all this. So when old Harpware was putting together his analysis of it, they were rejecting it. But suddenly when it was due to gravitational lensing for relativity, everyone was like, oh, no way. We found it. Einstein, super correct. So here we are now. So it was nice to be a hero, but only for a day. That was all right with me, though, because I thought that the pairing and the separation of the quasars made the ejection origin from the galaxies indisputably obvious. It was on, then off for the galaxy lensing, and then again for micro lensing. Lensing caused by small objects such as stars and planets within the galaxy. Yeah, dude, you got to watch out for micro lensing when you're taking these deep stellar obs. All right. When I heard that gravitational micro lensing calculations required a steep increase in the number of quasars with the fainter apparent magnitudes, however, I protested that the observed number flattened off as they become fainter, as shown from figure 7.1. Shows that only the brightest quasars have an increase steep enough to satisfy the prediction. When I submitted this to Astronomy and Physics journal, the editor was not about to believe it and required a letter from one of the leading lens theorists, Peter Schneider, to convince him that my argument was correct. I will always admire Peter for his integrity upon writing support for the opposing result. Dang, shout out to your boy Peter. Let's see. But what would I predict for a number counts for quasars as a function of their apparent magnitude? That was actually a pretty easy question, since if the quasars belong to a bright nearby galaxies, they were distributed in space in the same way, shown in figure 7.2, how the numbers of the luminous SB spirals like M31 and M81 increase with apparent magnitude, the crosses. The line segment shows how the various quasar surveys increase with apparent magnitude. The fit is extraordinarily good, especially considering the nonlinear shape of the two functions, even the details fit well. The adjustment in the apparent magnitude required to make the fit is very significant. For quasars that are 0.5 less than z, and when z is less than 0 or 1.0, the displacement is 10 magnitudes. This means that the quasars in the order of the 19th apparent magnitude must be found of the, this means that quasars of the order of the 19th apparent magnitude must be found around dominant galaxies of about 9th apparent magnitude. This is exactly what had been observed. In figure 7.3, for the quasars of 1.0 less than z and z less than 1.5 is shown to be also very good, but now the 0 point shift in the 11 magnitudes. This supports the general finding that the quasars become less luminous as they approach the redshifts of z near 2.0. It would imply that if one counts the number, it would imply that if the number counts of z near 2.0 quasars were better defined, they would require about a 13 magnitude difference with the associated galaxies. That would make it the 18th to 20th magnitudes, where z equals 2 quasars, generally visible in the association with only the nearest galaxies like M31, the Sculptor group, and M81. This is also what has been found, or this is also what had been found in the earlier investigations as summarized by quasars, redshifts, and controversies by your boy.
Yo, so I can take over from here. The audio is clicking super bad for me still here on Telegram. I don't know what's going on. So I can read for a bit, and then maybe we can just check and see if Discord has gotten any better.
Cool. Yeah, you're coming in good on my end, so.
Cool. So then
You
I'll
wouldn't be on
for
Linux, huh? Because popping might be Linux oriented in Telegram.
Yeah, it
Does
could be
Telegram
some
video
weird. Yeah,
chat?
it could be like a weird codec thing or something, but I'm not gonna mess with it at the moment. So my paper detailing the above analysis, Astronomy and Astrophysics, 2993-1990, lists 5 independent reasons why gravitational lensing cannot account for the excess number of quasars around the bright galaxies. But decisively, it demonstrates that the observed number counts for quasars can only be accounted for by their physical association with bright nearby galaxies. This would reasonably seem to have settled the question, but in a paper in Astronomy Journal 107-451, 1994, 2 authors reported a statistical association of quasars with foreground galaxy clusters. One of the numerous recent papers reporting quasar galaxy associations. They make the curious statement: we interpret this observation as being due to statistical gravitational lensing of background QSOs by galaxy clusters.
Quasi-stellar objects.
Thank you. Just one moment, please. All right, so galaxy clusters. However, this overdensity cannot be accounted for in any cluster lensing model and is implausible in any conventional model of cosmic mass distribution. More startling, they do not even reference the A&A paper from which we have observed here the figures which empirically disprove gravitational lensing for quasars. As papers multiply exponentially, one wonders whether the end of communication is near. Huh. Wow.
Yeah, nice. I like empirical evidence. That's my favorite kind.
Let's go ahead and do a little scrolly scroll. All right. The cumulative number of X-ray sources around. Whoa. We were still reading the bottom of that, or we were at the.
My bad.
Oh, I was reading that. Okay, never mind. I see where you were. So I was just reading the figure. It says the cumulative number of X-ray sources around Staffords, as in figure 2-1 or 2-1. The high luminosity SBs are plotted as crosses, showing again the same distribution in apparent magnitude as the excess X-ray sources.
Man, I do love every time you find something that turns out to break the model. It actually turns out to support the model, and that you predicted it all along with relativity every time.
Classic.
Every time.
Saved by Einstein.
We can test the distribution of X-ray quasars around Seyfert galaxies, which we found in Chapter 2, by means of the same number count diagram used above. Figure 7.4 shows the cumulative counts for the brightest SB galaxies, again as crosses. It is seen that they follow very well the excess numbers of X-ray sources associated with the Seyferts. This is as it should be because the bright SBs are basically the progenitors of the more active Seyferts and are distributed in space in the same way. Likewise, the quasars are associated with these galaxies, or the quasars that are associated with these galaxies show the same number count behavior with apparent brightness. In fact, these number count diagrams become the only statistical method of measuring extragalactic distances if the redshifts are not velocity. Therefore, they should become very important tools as time goes on. For example, at the moment, no one has the faintest idea where the mysterious gamma-ray bursters are located, but their number counts have a characteristic break resembling the break in the number counts for z=1 objects. That means they are probably distributed in space like the active z=1 quasars, that is, throughout the local supercluster. As this book goes to press, the gamma-ray bursters appear to be associated with faint active galaxies, one about z=0.8.
Dude, that's the Einstein cross that Alan knew off the top of his head in that debate one day? Really?
Yep.
Damn, dude. That's off.
Which also, by the way, yeah, shout out to Omnivore. He got like angry at me the other day and told me that I knew all about the Einstein cross and I was playing stupid and that he was going to prove that I was lying about not knowing about the Einstein cross. And I was like, no, dude, just go ahead and tell me about it. Like, I literally don't know. And he was getting really angry. And so I figured, okay, I guess I better learn about what the Einstein cross is so he can be right that I know about it. So, the Einstein cross. The most celebrated case of a galaxy supposedly splitting the image of a background quasar into separate images by means of its gravitational field is a rather unimposing object called G2237 plus 0305. When it was first discovered, it caused a panic because it was essentially a high redshift quasar in the nucleus of a low redshift galaxy. Quasars, Redshifts, and Controversies, page 146. Gravitational galaxy lensing had to be invoked for this one. Subsequent high-resolution observations showed 4 quasars of z=1.7 in the form of a cross approximately centered on a 14th magnitude galaxy of z=0.04. Since the 4 quasar images were all within 1 arcsecond of the galaxy nucleus, it was impossible to claim accident. But the gravitational lens was in big trouble from the start because Fred Hoyle quickly computed that the probability of such a lensing effect was less than 2 chances in a million. Huh.
Oh, that didn't sound very good.
All of this happening in an 1800th of a degree.
Well, you know, sometimes the galaxy or the universe, with the way the universe is splitting apart infinitely in faster than speed of light speeds, things just look a little crazy sometimes, Stone. But by the time I had already been curious enough to look hard at the publicity picture which NASA had released of the Space Telescope, picture of the Einstein cross. By this time I had already been curious enough to look. Okay, so it is an exemplary demonstration of how science proceeds when one realizes that thousands of scientists must have looked at that picture and said, oh, here is quasar image that has been split into 4 parts by action of one of those gravitational lenses. I was skeptical of gravitational lenses, and I looked at the picture and saw what should not be there. A luminous connection between one of the quasars and the nucleus of the galaxy. It is good to have friends you can trust, to be honest. I took the picture to Phil Crane and said, "Do you see what I see?" After studying it for a while, he said, "Yes, but I don't know if..." Scroll down a little bit whenever you're ready. "I don't know if it's real." "Well, how do we find out?" I asked. Fortunately, he was a member of the instrument definition team for space telescope imaging. He had all the exposure frames and processing tools in his computer. We contoured the image and tested against artificial stars superimposed near the galaxy. Not only the original connection, but extensions toward the other quasars looked real. One should carefully consider the following important question. What is the chance that a person who notices an important discrepancy in a scientific announcement has the opportunity to check it out at the level of the primary data? In the course of processing the images, however, we realized that by a stroke of good luck, there were 3 ultraviolet exposures with the space telescope in the wavelength band centered at 3400 A.
Angstroms.
Angstrom, you say? What did you say?
Yep, angstrom.
All right, angstrom. Thank you. 3400 angstrom. That band includes the Lyman alpha line of the redshifted quasars. This was the strongest emission line of the most abundant element in the quasars, and would most likely be to show any gaseous connection. Color plate 77 shows the breathtaking result. The western quasar D is connected directly into the elongated galaxy nucleus. There is absolutely no way to escape the overall result that the quasars are connected and generally elongated toward the low redshift nucleus. As if this was not enough, shortly afterwards, I was walking from an IAU session in Buenos Aires with Howard Yee at my elbow. "What's new, Howard?" I asked. There was a long silence, and then, "Well, there was something you would probably be interested in," he murmured. "What is it?" I politely asked. "Well," after some hesitation, he went on, "we put the slit of the spectrograph between quasars A and B in the Einstein cross, and we registered a broad Lyman alpha emission in each quasar. But between them, we found a narrow Lyman alpha line. It looks like there is some low-density gas at the same redshift as the quasars between them." A jolt ran through me as I looked at him to try and read the expression on his face. As usual in such situations, his eyes avoided mine. The point was, of course, that a line between quasar A and B passed directly between the nucleus of the galaxy and quasar D. On the face of it, high redshift gas was indicated near the nucleus of the low redshift galaxy. But what I knew, and what anyone can know looking at the Lyman alpha centered photograph in color plate 77, is that there is a putative. Is that Lyman or Lyman? Anyone know?
With Lyman.
Lyman. Okay. There is a putative Lyman alpha filament connecting quasar D to the galaxy nucleus. What the spectrum had confirmed was that this indeed was a low-density, excited hydrogen filament conducting the 2 objects of vastly different redshift. We are again seeing trails of material resulting from ejection and, as we saw in the first few chapters, tendencies for orthogonal ejection from the parent galaxy. Censorship at the critical point. Phil and I wrote all these results up in the best journalese style with all the tests, numbers, and references and submitted to the Astrophysical Journal letters. The editor sent it to a referee who had just written a long paper on the Einstein cross. He had been looking for the 5th image predicted by gravitational lens theory and had not found any convincing evidence for it, but concluded anyway that he had strengthened the interpretation as a lens. He wrote 3 reports trying to get us to say our results were all the result of chance noise, and then he rejected the paper. When I pointed out to the editor the conflict of interest with the referee's recent paper, the editor sent it to a theoretician with an even stronger conflict of interest. The latter essentially said that since fun, always fun stuff, since it disagreed with the current theory of the observations, or since it disagreed with the current theory, the observations must be wrong. The paper was finally published in a journal.
Theory beats observation yet again.
I feel very strongly about what happened, and I want to make my position clear. Astrophysical Journal Letters is the normal journal for publishing new observations from the Hubble Space Telescope. The telescope costs billions of dollars of public funds. The vast majority of paid charges which pay for the publication of the journal come from government-supported contracts. The overriding first directive of the editor is to communicate important new astronomical results. If the editorial process violates its primary responsibility, it misuses public funds. More scandals of the cross. Papers which claim the data confirms the standard theories, however, are rapidly published. Papers which claim that the data confirms the standard theories. Okay, sorry, my bad. Okay. One example of such a paper is Howard Yee's 1988 analysis, which computed a required mass of about 100 billion suns inside the very small radius where the quasars are located. This leads to a mass-to-light ratio of about 13, which Yee states is near the high end of that of large spiral galaxies, but it is entirely acceptable. Well, not quite. If you consider the original reference from Cormandy in 1988, you see that this this mass-to-light ratio is completely above the bulges for spiral galaxies, even above that for E galaxies. And that is for a lower limit on the required mass per light ratio. In fact, if you extrapolate the luminosity required for an elliptical to have this mass per light ratio, it comes out to MB equaling negative 25 mag. How bright is negative 25 mag? Well, conventional quasars start at negative 23 mag, so this galaxy would have to be 2 magnitudes brighter than the supposed brightest objects in the universe, a conventional quasar. In a later paper, Rix, Schneider, and Bashal in 1992, in a computation essentially no different from Yee's, derived the exact same mass for the galaxy. Their contribution was to change entirely acceptable to lens models. Explain the wealth of observations elegantly. Actually, this so-called confirmation rests on the assumption that the redshift dispersions in the galaxy interiors represent both velocities and velocities in equilibrium. As we have seen, the observations show this is incorrect on both counts and systematically overestimates the masses of the galaxies. Furthermore, the mass needed for lensing is underestimated by assuming it is all concentrated at a point in the center of the galaxy, hence the lower limit mentioned above. Also, in the matter of the cross, a disk galaxy is called an elliptical, and mass-to-light ratio comparisons are shuffled between blue visual and red. Even after all, this one requires an extraordinary and unprecedented galaxy to satisfy the lens requirements. Wow, so it's brighter than the brightest thing in the universe, and just really, really, really massive, huh?
Science.
Cool. For realistic galaxy masses, gravitational lens effects may someday show up, but on a much smaller scale than currently claimed. You have a lot of faith, Mr. Arp. As for the central galaxy in the Einstein cross, one only needs to look at it to realize that it is in fact a small dwarf galaxy. I think it would be an enormously helpful reality check if astronomers studied galaxies in groups and learned to judge the giant, medium, dwarf characteristics of a galaxy from its morphological appearance.
Dude.
Wow.
Turned out to
Seriously,
just be a
absolute
dwarf.
magnitude. Absolute magnitude is a scam.
Are you challenging the golden ladder ratio, Stone? How dare you?
I did it with a video.
Oh, did you really? We have to watch that at the end of this.
For sure. A couple thoughts about stars. Yeah, man.
Oh,
Sounds
how
great.
have I not seen that? Fantastic.
I don't know.
Oh, dude. Yeah, we're definitely watching that after. Sorry, go ahead and continue, Toby.
Cool. So the general case against lensed quasars. The ARP Crane paper on the Einstein cross also made clear that a basic requirement of gravitational lensing had been violated by all the observations of quasars. The, the theoretical calculation in Figure 7.7 show that the lensed image would need to be elongated by a factor of 4 to 5 to 1, or from 4 to 5 to 1 along the circumferential direction. This is just common sense because, as was mentioned in the beginning of this chapter, people originally started looking for gravitational rings around deflecting galaxies. In the more common case, where the lensed object is not exactly behind the lens, the ring degenerates into segments of rings or arcs. The fact that supposedly lensed quasars never looked like arcs was always excused on the basis that they were unresolved point sources, i.e., if one could get enough resolution that then they would be seen as arcs. But figures 7.5, 6, and color plate 7.7 of the Einstein cross show that the images are well resolved, and instead of being arcs, the quasar images are extended back towards the central galaxy. As a result, lensing of any quasar was excluded from the beginning because the theorists forgot their own theory that quasars were nuclei of host galaxies. Even if the nuclei could not be resolved, the host galaxy was supposed to be of the order of 40 kpc in diameter.
That'd be a kiloparsec.
Oh, thank you, sir. The order of 40 kiloparsec in diameter, and since its surface brightness was preserved under magnification, it should have been quite visible and noticeably arc-shaped. Recall that 3C48, the first quasar discovered, was supposed to have a host galaxy of 12 arcseconds in extent around it. 3C48 was about 16th apparent magnitude. Should we believe that all quasars of comparable redshift at 19th apparent magnitude with less conspicuous nuclei would not have had conspicuous host galaxies on the conventional assumption of redshift distance, and not an arc among them? We are just about to get into the subject of high redshift arcs in clusters of galaxies. They are supposed to be hugely distant background galaxies lensed by the gravitational field of the cluster and drawn out into thin, conspicuous arcs. If this is true, the enthusiasts cannot have lensed objects at the same redshift appear both at point sources and arcs. They simply cannot have it both ways. So the redshift is in arcs, and the presumed lensing is in
Arcs
pulled
as well.
inwards. Is that
No, it's that
Point-
the
point
lensing
source.
is in arcs and the shift is in frequency.
point source, as he says? So I can keep reading here.
You want me to
Actually, can
spell
we
you off?
try switching back to Discord? See if it's any better.
Yeah, we can
It's been 40 minutes.
take a gander.
Yeah, go for it.
Testing.
Nice echo.
Testing.
Oh, because I'm still not muted on Telegram. My bad.
You're straight.
Or did the call get ended?
I'm not sure. I left because I could hear your thing, and I was like, I don't want to hear it anymore. While we were waiting.
Gotcha. This seems like
I
it's
might
working
Yeah,
for the moment.
Seems all right.
Cool. Does someone else want to try reading?
Yeah, we have a special
give it a
guest
shot.
that's going to come in and do a drum solo. I heard in the chat. I'm just kidding. Go ahead.
Oh, is that so?
No. God help us. No. All right, here we go. Stone.
Arcs and arclets in clusters of galaxies. When Roger Lenz first registered arcs in a deep photograph of a cluster of galaxies, he did not pay much attention to them. Hold on a sec, let's get a bigger frame going for me here. There. Later, they were highlighted by Vahe Petrosian, but it was not until the redshifts of some of them were measured as being very high that the idea that they had to be gravitationally lensed arcs of distant background galaxies became mandatory. I was suspicious of this interpretation because I felt high redshift objects were generally not so distant, and I also because I felt the galaxy clusters had much smaller masses than conventionally estimated from the redshift dispersions of their members. But I had to admit that the fairly accurate arc shapes centered on the clusters looked like the expected degenerate Einstein rings and made a very persuasive case for gravitational lensing. When the evidence for very small nearby Abel galaxy clusters, which was presented in the preceding chapter, began to sink in, and it took some effort to change, It took some effort to change my perception of them. I realized it was impossible for them to have enough mass to lens any distant objects. Taking a more critical look at the observed properties of the supposed lensing clusters revealed some very surprising properties. For example, A370, pictured here in 7.8, has a redshift of z of 0.375. Not only is this close to Z.3, redshift peak for intrinsically redshifted quasars, but if we were to try to fit it to the redshift apparent magnitude diagram for Abel clusters, we would find it had an excess redshift of about 30,000 kilometers per second. Peculiar velocities of this order of magnitude are simply not contemplated for the conventional Hubble flow. Moreover, A370 is only 1.7 degrees away from the large active Seyfert NGC 1068, which was found to be a source of ejected quasar candidates in Chapter 2. In fact, the elongation of the cluster points right back to NGC 1068. Hold on a sec, my cat's trying to knock things off the desk. Bad kitty. Okay. Another cluster with supposed gravitational arcs, A2281, has a more reasonable redshift of 0.176 for the apparent magnitude of its members. But that's the same redshift of some of the clusters and BLAC objects running down the spine of Virgo and Fornax clusters. Go away, cat. Stop knocking my stuff off. In fact, A2281 is only about 1.3 degrees away from 14.46 absolute magnitude Seyfert galaxy of Z 0.026 and only 25 arc minutes away from a 14.3 magnitude spiral of unknown spectrum. Still another cluster with supposed gravitational arcs is MS0440 plus O2, pictured in 7.9. The arcs don't look like an elongated background galaxy. They look like an ejected shell. What is more, in this case, there is a Seyfert galaxy only 22 arc minutes away from the Arby's down the street.
Nice.
Go get it. It's on sale. Scroll, Alan. Thank you. With essentially the same redshift from Z.196 to Z.19. Obviously, they are a pair of active galaxies, but one has more companions plus a shell. Just casual inspection shows these active clusters lie strikingly closer on the sky to low redshift and active galaxies than they should be by chance. Again, it would be of the highest priority to systematically test the correlation between these clusters and catalogs of various kinds of galaxies and quasars. The development that really shocked me, however, was the report of radial gravitational arcs, i.e. arcs that pointed back to the center of the cluster rather than tangential to it. That was exactly the opposite to the expectation of degenerate Einstein rings. All right, radial gravitational arcs. Figure 710 shows the prize exhibit, the cluster MS2137.
Yo, hold on a second,
with a supposed.
Hold on
Hey,
a second.
what up?
So the Einstein ring
Am I going too fast?
No. So the Einstein ring goes in the opposite direction, and they were like, hey, boys, this is definitely confirmation of our theory. And it doesn't even go in the correct direction.
Its motion is 90 degrees out. Yeah, the shape is completely off.
Oh my god, dude! I wish I had read this before the debate. I didn't even know much about that stuff. I just thought it was all fake. That's hilarious. It doesn't even go in the same direction, dog. What a disaster for your model. Oh, you think the sky's lensing in accordance with the laws of Einstein, bro?
Everything about about the Einstein cross. Oh, I'm muted.
Yeah, we got you. We got you, Toby.
Everything about the Einstein cross, like what they were saying earlier on too, with the values as far as the distance and the magnitudes. Everything about that was off. Like
the mass was off, the magnitude was off, everything is off. The proximities for lensing to occur was off. The orientation of these arcs is off. Absolutely every last prediction they've got based on Newtonian is off. I wonder why that is.
Wow, dude. And they banned this guy.
Okay, let's step up to the punchline.
Yeah,
sounds like he's saving the best for last here with radial grav arcs. Figure 710 shows the prize exhibit, the cluster MS213723 with a supposed radial arc emerging from the central galaxy and aimed directly at the middle of the tangential arc. While I was trying to get over this latest example of our theory thrives on adversity bravado, something was nagging at my memory. I wonder what it could be. Where had I seen this before? Then it struck me. The longest, straightest jets emanating from a spiral galaxy, NGC 1097. Of course, color plate 27 shows in true color that the strongest of the 4 jets ejected from this extremely active Seyfert ends in a right angle, dare I say, tangential arc. The right angle turn of the main jet in NGC 1097 was always a perplexing mystery to people still trying to embrace the ball theory. Yeah, I suppose it was jokingly called the dogleg jet, but it was obviously ejected. Could it have hit a cloud or piled up material ahead of it and then flattened at a right angle to the direction of propagation? Yeah, probably not, hey?
Dude, yeah, that old trick.
Was there any other example like this, as in the entire sky? Why, yes! There was the second strongest jet from a spiral galaxy, the one from NGC 4651. When I was reducing the X-ray observation shown in Chapter 1, I wanted to get the deepest possible photograph of the galaxy in order to understand the relation of the jet to the nearby apparent ejected quasar. The best possibility was the deep 3AJ survey in progress with the Palomar-Schmidt telescope. I am extremely grateful to Bob Brucato for sending me a copy of this object before the survey was formally released. Ooh, insider stuff. The limiting exposure is shown here in Fig 711. I'll go get a Slim Jim. Lo and behold, the ejected jet ends again in a tangential arc, just as the NGC 1097 case. So one would conclude empirically that the galaxy cluster in Figure 710 was also ejecting a jet, which was responsible for an arc of similar material at right angles to its end. Note also that this galaxy cluster is of the type where one galaxy is dominant and the remainder are very much companions to it, the kind often involved in ejection activity. Also note how the low surface brightness of the arcs in clusters render them very difficult to discover even with the deepest photography. Then match that with the characteristics of the ejected jets from the spiral galaxies just discussed, which are also only discovered on the deepest photographs. If you look for what is being ejected in figure 710, it turns out to be a quasar of Z 0.646. The cluster is 0.313. This quasar is at a, now that's, I don't know what that is, something angle of negative 22 degrees and only 49 arc minute distant. In fact, it comes out right along the fat jet, if that's what it is, which is visible in figure 710. Notice that the central galaxy in this cluster is dominant. What you actually have here is an active galaxy surrounded by many companions. Oh, my cats are beating each other up. What the hell? Knock it off, guys. God damn. Just clamoring for attention. Notice that the central galaxy in this cluster is dominant. What you actually have here is an active galaxy surrounded by many companions, which is currently ejecting in the direction of the arcs and the quasar. We shall see in the next chapter that the redshift of the central galaxy in the cluster and the quasar are very close to the quantized redshift values of 0.3 and 0.6. You guys want some more? Diametric arcs in a galaxy cluster. In a redshift measurement program of X-ray clusters discovered by Rosat, the most luminous cluster was on the conventional interpretation redshift RxJ, what is that, 1347.5, 1145, which what this means in operational terms is that this cluster represents the most extreme deviation from the redshift, X-ray intensity, Hubble relation. Get her down there, huh? One more. Keep on flowing. These dots are meaningless unless they're in color. And
okay. I just wanted to look at the dots. My
connected-
bad. Sorry.
they're just, it's just so pointless staring at a bunch of splotches, man. I could have puked on the wall. It would have looked more meaningful. What connected with this extreme property was the unique finding of two short arcs diametrically spaced across the more compact of the two bright central galaxies. The picture of this galaxy cluster and its arcs is shown in figure 712. The eye is immediately struck by the blotchiness, by how short the arcs are and how exactly they are aligned across the galaxy. This is strongly similar to the quasar pairs ejected from active galaxies as presented in chapters 1 and 2 and suggests the question: what would happen if a quasar in formation or entrained material in the ejection encountered resistance in the direction of its motion? Would it flatten as it became more luminous? If it is a lens, why are the arcs so short? And why is the circular symmetry broken in this opposed even fashion? What about the equal spacing of the two across the galaxy? By some unexpected coincidence, there's a bright magnitude and absolute velocity V quasar at Z 0.34, about 45 arc minutes northeast of the compact central galaxy. 45 arc minutes. That's 3/4 of 1 degree, guys. The alignment is within about 15 degrees of the alignment of the two short arcs. Since the redshift of the cluster is 451, the implication would be that it was ejected from the quasar as a strong radio source the quasar may have, BL lack properties. Regardless of the significance of this latter association, however, the cluster is a prototype of the ones we were discussing in the previous chapter. It is extremely strong in X-rays, located in the supergalactic plane between Virgo and Centaurus, CFIG 616, and just the kind of object we would consider to be a young, active object ejecting and breaking up into smaller, intrinsically redshift young galaxies. Everybody following on? Grab your crayons. Galaxies which eject shells and arcs. At this point, we would like to show some pictures of real galaxies which are clearly ejecting material which uncannily resembles the claimed gravitational arcs. First, there is an extended cluster of galaxies called the Hercules cluster, oh, swell, which contains many disturbed and active galaxies. Some of them have mood disorders as well. 713 shows one of these, which has a conspicuous jet emerging from it. It's not even wearing a tie. There is no question that this feature belongs to the galaxy because the knots in the tie of the jet have more or less the same redshift as the galaxy. Ooh, Victor, Ambarzoomian in the 1950s presented this as an example of new galaxies being formed in an ejection. This is almost like stellar porn. But of key importance for the present demonstration is the thin arc of luminous material to the north-northwest of the galaxy. This arc is actually connected back to the galaxy by a diffuse filament of luminous material. It is clearly also an ejected feature. Closer to the galaxy on the southwest side is a fainter, thinner arc which continues around very faintly in a roughly circular fashion as if it might join the stronger arc to the northwest. There are indications that deeper photographs would reveal further luminous arcs which are essentially identical to the proposed gravitational arcs in clusters, but in this case are clearly a result of explosive activity in the central galaxy. This is cool. 714 shows another galaxy that has 3 distinct arcs on one side and a long presumed ejection tail in the opposite direction. The 3 arcs are evenly spaced and concentric, suggesting a ripple or vibrational impulse from the center of the galaxy. Anybody want to talk about periodicity? Good luck. As a final example, 715 shows a deep photograph of a galaxy which has such sharp edged circular arcs that it suggests a bell ringing or vibrating underwater. How about that? A little bit of sonoluminescence just slowly creeping into your eyes, just slowly creeping in. Similar galaxies, and particularly this one, have been modeled as 2 galaxies merging. But in an encounter, the best one might expect is one galaxy spiraling into another. Oh, good pun. As noted, however, the pictured arcs are not spiral, but perfectly circular. So like they got out their compass and shit. Moreover, as the picture shows, there are at least 2 faint jets emerging from the center which testify directly to the ejecting explosive nature of the nucleus. This is so Niels Bohr atom nucleus stuff applied to gargantuan scale. Ejection of arcs and from Seyfert's. The remaining question is whether ejected arcs can be composed of material which is of considerably higher redshift than the ejecting galaxy. One would naturally think of the Seyfert galaxies which eject quasars of the same order of redshift as the supposed gravitational arcs measured in the galaxy clusters. 2 investigators, Rob Forsberry and Andrew Wilson, among others, have shown that Seyfert galaxies characteristically eject material in opposite directions in cones of various apparent opening angles. The most recent and spectacular example of this is shown in plate 715. The crucial aspect of this observation is that it shows that the material in the ejection cones is coming out in a series of concentric arcs. Oh, baby. The arcs appear to be getting thinner as they progress outward, perhaps as a result of shocks or compression by faster following material. When a high redshift quasar or proto-quasar is being ejected, there may well be similar age material which trails the quasar and forms arcs. Or the quasar itself with low particle masses may be deformable into an arc if it treats clouds or medium in the neighborhood of the galaxy. Oh, it meets clouds. Sorry, not treats them. It meets them. How do you do? The last would be a possible model for the previously discussed short pair of arcs across the galaxy in 712. Of course, some arcs would be expected to be entrained material of the ejecting galaxy and some arcs new young material of high redshift. So it would require a careful spectroscopic observational program on these kinds of objects in order to check this working hypothesis and modify it if necessary. What are the odds of that? The important result, taking everything so far, seems to be that active galaxies eject high redshift quasars and also eject diffuse material, some of which is in the form of arcs. Since many able clusters of galaxies are energetic X-ray sources and contained active galaxies or galaxies perhaps recently active, it's reasonable to suppose that they also could eject material that would appear as high redshift arcs. This is just so confirmational, you know what I'm saying? The small size of clusters, which we found in the preceding chapter 6, however, would seem to preclude the ejection of anything initially massive. Regardless of which is the optimum new model, however, The observations clearly confound our conventional assumptions. I'm shocked. Okay, I'm good for now, guys. You guys want to do some?
Dude, that was awesome.
Yeah,
Thank you.
Yeah, that was
Thanks,
excellent.
man.
So I can pick back up.
I'm game too.
Go ahead if you want to. Sounds good.
Yeah, sure.
Scott, my man, what's up?
Yeah, tear it up, man. Tear it up.
Okay, cool. All
Get
right.
in there.
This is going to be fun. Ejections from able clusters of galaxies. Because I was alerted by all the pairs of X-ray quasars we had been finding across Seyfert galaxies, when I first ran across the X-ray map of the cluster of galaxies shown in figure 7.16, all I could see was the pair B and C across the central active galaxy. Actually, this is one of the best known galaxy clusters, the Centaurus cluster. Since the two sources are aligned within the accuracy of measurement across the central galaxy, it is highly probable that they have been ejected. I immediately took the listed positions of these sources and processed them in the automatic plate measuring program. Source A is identified with an 18.7 mag BSO. What's BSO? Possibly.
That's a good
Oh,
question.
that's stellar object. It's B
It's
stellar
something
object.
stellar object.
Yeah, wasn't it quasi
Binary, maybe?
stellar object or whatever?
Bogus.
Yeah, let's go with that.
Probably binary.
I can look it up real quick.
I'll keep going, I guess, while you do that.
Yep.
Yeah, go.
Okay, 18.7 mag BSO, possibly variable. Source B is identified with a 15.6 mag blue compact galaxy, almost certainly of much higher.
Stellar object. Sorry to interrupt. It's blue.
Oh,
stellar
blue.
object.
Okay.
That makes sense with what you're reading there.
Yeah, true. Blue compact galaxy, almost certainly of much higher redshift than the central galaxy. Source C is either a 16.7 mag galaxy or a 17.1 mag BSO, fuzzy, or a 20th mag object. It will require a spectroscopic program of observation to obtain redshifts and identifications and perhaps a check position on C. Such observations could easily be obtained with current 10-meter class telescopes, but this is the last thing one would expect to happen because they are completely occupied with really important projects. I may go to South Africa to try to measure the candidates with a 1.9 meter telescope. It is the same telescope I used to set distance scales to the Magellanic Clouds 40 years ago. So this guy's been around a while. Moved to new locations with an aluminized mirror instead of silvered and a modern spectrograph. It would be some satisfaction to leapfrog the intervening years to a better understanding with the same telescope. Oh, and there are several important comments that should be made about this cluster. The first is that it is a cluster of galaxies dominated by one active radio galaxy, NGC 4696. The redshifts of the rest of the galaxies in the cluster average 375 kilometers per second higher. This is the same situation we found for all groups involving companion galaxies in Chapter 3. Secondly, the cluster is the rich, bright Centaurus cluster, which was specifically associated with the giant Cen galaxy in Chapter 6. We can see the cluster in Figure 6.7, labeled Z equals 0.011, almost due west of Cen A. As Figure 7.16 shows, fair enough. As figure, I agree too. Without the color to excite them, it's kind of bland. The gray pictures. As Figure 7.16 shows, the Centaurus cluster is elongated back in the direction of Cen A in the same direction as one of the two exceptionally strong opposing absorption lanes, which emerge from the center of that extremely active galaxy. The implication, as in previous cases, is that Cen A ejected NGC 4696 along the line of that lane, and NGC 4696 then gave rise to the surrounding cluster, which is in the nature of later generation companions to it. It is perhaps significant to note that there is a 13.9 mag Seyfert galaxy of Z equals 0.016 near NGC 4696 on this same line back to the western lane in Cen A.
I got a Newtonian question about all that. And that is, how is one thing ejecting something else that's so freaking large? First off, where is it getting the spare mass what is the thing? What is the pressure-oriented thing that is driving the ejection to begin with? And finally, what about gravity? Shouldn't gravity also be pulling these things inward to, decrease entropy to create more round ball-shaped things? What about
Is,
gravity? And
is
this
that
is
is
why
that
they
where
talk
the
about all this mass they're not
uh,
finding, right? It's crazy. And I remember Franco a few nights ago when we were talking about the model, talking about particulates and subatomics, all the leptons and all the ones he loves talking about. And every time somebody challenged him about the model, he says, yes, but we're going to improve the model. We're always trying to redesign and repair the model and update the model. It's like, no, man, toss the fucking model out.
yeah, they've been
It's
repairing and
it's
updating the model
done.
for 100 years. Yeah,
Shoot the model.
yeah, it's a disaster at this point. Uh, oh, but as far as what's causing it to push out, isn't that where they're invoking the lensing, the gravitational lensing? Is that perhaps would be
No, that's
one?
the light bending one thing around a closer thing coming to us. They like to play
Okay,
that
yeah,
game with
right.
the
That's
sun too, right? Yeah.
right. Yeah, the lensing is not gonna give it that explosive oomph.
No, it's going to
Actually, I had one of
distort.
right. When they reference the Z, is that like a brightness thing?
That is your redshift value. They're talking about relative to stationary objects and in what percentage the frequency coming at you in a Doppler analysis would change. There's a ratio there, much like a refractive ratio is
Gotcha.
expressed.
So it's sort of the amount of red shifting going on.
And that's
Uh,
all hocus too, man. It's just mind blowing where they're going with it.
yeah, yeah. Okay. Uh, so continuing. This cluster is so spectacular an X-ray object that it was featured in the Rosat calendar for 1995. Back to the sort of pornographic. They've even got
No
a sexy
way.
Yeah, I
They
heard it
got
was very sexy shot for June that year, I think.
for
Yeah.
Rosat.
they got centerfold, I heard.
Yeah. Uh, it was there that the pairings of X-ray sources across it leaped out at me. Figure 717 shows that the bright sources A and E are paired across the center of the X-ray emission. F is cataloged as an 18 mag, Z equals 0.253 active galaxy. The redshift of the cluster is Z equals 0.0528. A can be identified with a bright galaxy. It will be fascinating to obtain the redshift of that galaxy since it is obviously the counter ejection object to E. But even more sensational is the X-ray source D. It is connected back to the cluster interior by a luminous X-ray filament. It is cataloged as an 18.3 mag active galaxy with Z equals 0.129. Naturally, I looked for the counter ejection, and there it was, an extension outlined by many X-ray contours leading to a sharp point at about B in figure 717. On the Deep Schmidt photographs, I looked in that vicinity for a candidate object. Just as I was about to give up, at a little further along the line than I was looking, I spotted a double star, one component of which was blue. I'm betting that is the quasar opposite D. Of course, it has to be confirmed, like everything.
And that's
Uh,
when you know you're in Deep Schmidt.
Deep Schmidt, indeed. So now we have a cluster from which 2 ejections of high redshift objects have taken place. This and the previous case of an ejecting cluster were found serendipitously. It obviously would be highly profitable to systematically examine strong X-ray clusters for similar cases. An example of one such possible finding is the following. The galaxy cluster associated with NGC 5548. In the systematic survey of bright Seyfert galaxies discussed in Chapter 2, one very strong X-ray cluster was found apparently ejected from the very strong Seyfert NGC 5548. Figure 718 here shows the archived X-ray map processed by ARP and Radecki. It is clear that a strong pair of X-ray sources is paired across this galaxy cluster of Z equals 0.29. The Quasars happen to be cataloged and have redshifts of z equals 0.67 and 0.56. As discussed previously, this correspondence and properties essentially assure them of being an ejected pair from the galaxy cluster. Of course, there may have been a single object at z equals 0.29 at the time of the ejection of the z equals 0.67 and 0.56 pair. In the act of ejection, it may have broken into the small cluster objects we presently see. Although many more cases need to be investigated, the results so far seem to assure the phenomenon of galaxy clusters ejecting higher redshift objects. The hierarchy of redshifts in the various associations also confirms the working model of larger, older galaxies, bringing forth the original ejections and then the younger, higher redshift offspring, giving rise to even higher redshift ejections.
You got to
The
keep them
galaxy clusters
separated.
the galaxy clusters seem to be able to eject quasars up to about z equals 0.6. But by about z equals 0.3, the progenitor quasars and BL lac objects seem to more easily break up into smaller galaxies and form clusters. Both the quasars and these galaxy clusters, however, are much closer, smaller, less luminous, less massive, and much younger than conventionally assumed.
What a pile.
Yo,
Before
Shane,
we get past ejection, I'm back now. Cool. You
Yep.
hear me now?
Yes,
Sorry,
sir.
I was trying to chime in, dude. I used to laugh at ejection jets, but I think that's like an aspect of a magnetic toroidal field. The dude in the plasma, the primer fields emulated that with two bulb magnets, and he had like little magnetic balls being shot out the top through an ejection jet that he literally created with the forced magnetic field. So I think that's kind of real, but I think that what they're talking about is retarded.
Yeah, that's a really good point. As we've been reading all this, that's kind of been in the back of my head, like, oh, that would be easily explained with just, magnetism essentially in the sky.
Yeah, dude, a lot of the primer fields is him understanding magnetism and properly describing all the things in the cosmos. That's why, like, when I say he debunks gravity and black and dark matter, it's because he looks at it and he just describes all these, quote, quasars and ejection jets with, like, magnetism. Oh, and look, it makes perfect sense. So,
Like, so much of what...
Who does that?
David LaPont, and from the primer field, there's like a mini series on YouTube that everyone should check out.
Yeah, can you
That
link
all-
that, please?
Nice. Yeah, it sounds cool. But just in general, right? Like, it's like everything he was saying, especially when he's talking about like the Einstein cross and all of the ways it didn't line up, is just like, oh, well, that sounds quite magnetic. That sounds quite toroidal. Oh, yep, that sounds quite toroidal. But yeah, anyways, whenever you're ready to continue.
All right. The archetypal coma cluster of galaxies. The coma cluster represents the densest, most conspicuous aggregate of galaxies in the sky and has long been taken as the prototype medium-distant galaxy cluster. Sinclair Smith was one of the first astronomers to calculate under the assumption that the redshifts were velocities in equilibrium, virialized, that the mass of the cluster far exceeded the mass of the galaxies composing it. Fritz Zwicky later emphasized this discrepancy, and so was born the concept of dark or missing mass. I knew that name, Fritz Zwicky. Yeah, he's the source of dark matter. Fun in games, huh? I think.
Yep.
Anywho, this observationally undetected but crucial repair to the theory had to be invented to save the redshift equals velocity assumption. Eventually, it became so needed that today we have a universe. Eventually, it became so needed that today we have a universe which is reported to be about 90% unobservable. The first thing one should notice about the cluster, however, is that the brightest galaxy has a redshift of z equals 6,456 kilometers per second, whereas the mean of the rest of the galaxies has z equals 7,000 kilometers per second. This is an extreme case of the companions having systematically higher redshift and therefore a considerable component of non-velocity redshift. Bye-bye dark matter. Also, the intrinsically redshifted galaxies in young non-equilibrium clusters, e.g. X-ray clusters, become much less massive and therefore less able to lens background objects and more like the low redshift quasars and BI lac objects to which they were related in Chapter 6. But the X-ray map of the cluster shown in figure 7.19 is a real shocker. Far from an equilibrium distribution of X-rays, the cluster is extended with strong X-ray sources on either end of the extension. The strong source on the southwest extension, note the isophotal elongation toward it, is not identified. But the strong source to the northeast is an active galaxy, high, with a redshift of z equals 0.029. In this same direction lies the strongest point X-ray source within the area of the cluster, X Comae, with a redshift of z equals 0.092. Why should an active galaxy bright enough to be named in the variable star catalog fall right in the Coma cluster? Why should these events always be explained as accidental background objects? But then why should the Coma cluster have always been assumed to be a prototype cluster when it is a unique aggregation of lenticular and E galaxies without the usual complement of other morphological types to give some hint of their luminosity? As Zwicky sagely remarked, it takes a large number of stars to make a spiral galaxy, but only 3 to make an E galaxy. I guess that's sage. Since we do not have any redshift or morphological criterion for its distance, the best evidence seems to be its location in the sky, where it forms an obvious northern continuation of the Virgo cluster in the supergalactic plane.
Another gigantic assumption.
XCOM is a 16.65 mag Seyfert 1 galaxy, much like those found in the Virgo cluster, e.g. Bubba. And looking around, it furnishes some stunning proof of the association of quasars with Seyferts. As figure 719 shows, almost all the point X-ray sources are clustered around XCOM. They are cataloged quasars with their redshifts written next to them in the figure. The redshifts are in the expected range and they form a rough line through the Seyfert galaxy. It would be very interesting to identify and measure the X-ray source just to the northwest of XCOM along this line. Altogether, the Coma cluster confirms in general and in detail what we have learned about clusters of galaxies. Instead of being old quiescent systems, they are filled with high-energy radiation that requires resupply. They show strong evidence for recent ejection of higher redshift matter. They have large components of intrinsic redshift. They are small and low luminosity and are associated with older, more nearby galaxies.
About that resupplying thing, like I was saying before, where from?
Yeah, good question. Just vacuum, I guess, resupplying. So, yeah, I'll hit another one here. And if anyone wants to jump in, just pipe up.
If you want to keep going, please do. We're getting pretty close to the end of the chapter, so yeah, feel free to.
Okay, I can knock it out.
Feel free to tag me in if you want to, if you want to at any point. But otherwise, feel free to finish it up. Either way, it's cool with me.
Heads up,
All
that's
right,
a right ascension and declination call at degrees, minutes, and seconds coming up to you.
Oh, okay. That's exciting news. All right, the Hubble Deep Field. In a courageous assignment of discretionary time, the director of the Space Telescope Science Institute, Robert Williams, assigned 150 orbits of the Space Telescope to deep photography of a single 4-square arc-minute field at RA equals 12 hours, 36 minutes, 49 seconds. Declination equals 62 degrees, 12 minutes, and 58 seconds. Position calculated for equinox 2000. This reached objects of far fainter apparent magnitude than had ever been seen before, about R equals 30 mag. The resulting picture is shown here in plate 720. There are obviously a very large number of very peculiar and unusual galaxies in this field, but even after examining over 77,000 galaxies in the ARP-MADOR catalog of southern peculiar galaxies and associations, I did not appreciate just how peculiar the galaxies in the deep field were until I performed a galaxy-by-galaxy classification on the same system of the previous catalog of bright galaxies. Table 7.1 here shows that while 95% of the nearby galaxies have normal, regular morphologies, only 11% of the deep field galaxies could be considered normal in appearance. I sent this report to Nature, but even before John Maddox left the editorship, the magazine had elevated itself above simple observational results, and it was not published. My friend and classification expert, Sidney Vandenberg, added another important result, namely that there were almost no normal grand design spirals in the deep field. As might be expected, some of the redshifts measured very high, going into the range of z equals 3 to 4. What does this mean in terms of what we have found out about the nature of redshifts? It will be shown in the theory chapter upcoming that our interpretation of the redshifts agrees with the conventional interpretation in that we both agree that a high redshift object is very young. In the conventional view, they are far away, and the long look back time shows how they looked when they were much younger. In our interpretation, they are the same young age, recently created, but can be quite nearby. The essential difference is really that our newly created objects are low luminosity and the Big Bang young. Objects are very luminous because they must be seen at a great distance. So the question comes down to, are the young objects seen in the deep field low luminosity or high luminosity? Empirically, the highest luminosity objects we know without recourse to redshift distances are the regular SB spirals. We would generally expect the most luminous objects to be the most massive and therefore the most relaxed equilibrium forms. This is one thing the Hubble deep field objects are not. On the other hand, the quasars we interpret as young, low luminosity objects tend to be high circular diameter objects. Would even lower luminosity quasars at high redshifts look like the Hubble deep field objects? Could 3C48 and the quasars examined for host galaxies with the Space Telescope be comparable? This would be an interesting point to discuss in detail. But one remark in this direction is that the tendency for young, nearby, low luminosity objects to break up, eject materials, show jets, and disturbances could explain the prevalence of linear, knotty objects and multiple objects as observed in the Hubble deep field. Richard Ellis has studied the Hubble deep field in detail. He finds a large number of a new kind of low surface brightness, peculiar galaxy. On the conventional interpretation of redshift, they are of high enough luminosity that it is clear that there can be no local counterparts of such objects. But isn't it required then that they be nearby, low luminosity remnants of more recent formation, which have higher intrinsic redshifts because they are young? This is an important point because our evidence has been going in the direction that all objects we can be sure of are within the rough confines of the local supercluster. But are there any objects appreciably beyond the local supercluster, or is there empty space for an unknown distance? On the interpretation of redshift, this book uses there could be very distant objects of any redshift, but they would have to be luminous enough so that we could see them at great distances. If there is an upper limit to galaxy luminosity, we may not have seen any so far. If we go fainter, as with the Space Telescope, we may see some if they are there, but how will we recognize them amongst the welter of nearby objects? An amateur spots the crucial patterns. Empirical pattern recognition, which has so drastically changed our view of extragalactic astronomy in this book, is based on the recurrent evidence of pairing of active objects across large low redshift galaxies. The tyranny of the observations is to insist on opposite ejection of extragalactic material as a ubiquitous process that operates on all scales. How is it possible that the exquisitely trained professional scientists have not recognized this evidence? How indeed.
Gasp.
To make this point that to make the point that it is not the evidence but the viewer that is the key here, I want to present figure 720. These are examples from a page which an architect named Leo Vuk sent me. He just Xeroxed out the pictures which he found in astronomical publications which showed the same theme over and over again. He drew in the lines like the delightful childhood game of connecting the dots together to get the picture. None of us have the correct theory, but the professional tends to interpret the pictures by using the theory he was taught, while the amateur tries to use the picture to arrive at a theory. The real-life story of the exploding radio galaxy 3C227. I sat down at lunch across from a longtime acquaintance of mine from a neighboring institute. "Oh, Chip," he said, "you'll be interested in an object in the midst of a disturbed galaxy I'm analyzing." A few weeks later, he said, "There is an emission line which seems to indicate the object has a lower redshift than the radio galaxy." I replied, "I cannot understand that. I would expect it to be higher. Many months later, he reported, "Oh, that object turned out to have a higher redshift." For years after that, every time I passed him on the grounds, I urged, "Bob, you should publish that observation. It is very important." After a long time, I had finally forgotten about it when a reprint appeared on my desk. I remember thinking, is this the object? Rapidly, I scanned the pictures, trying to spot the object. No luck. Finally, I located a small diagram on which an object was marked BO. What is BO? I wondered. I could only think of an advertising jingle from my childhood. Lifebuoy soap fights BO, body odor. Then I found at the end of the figure caption, BO indicates a background object of redshift of Z equals 0.3799. It took some time for me to figure out where I was on the picture of the disturbed radio galaxy, which had a redshift of Z equals 0.086. It was amazing. It was only 11.
Scroll
arcsec from the center of the explosion. That meant the chance of finding a background quasar was only about 3 in 100,000. On the other side and further out were some compact galaxies of about Z equals 0.129. It was a more or less perfect example of an ejection into the dense part of the galaxy, which had ripped the galaxy apart and slowed down the escape of the high redshift object, as suggested in Chapter 3. Would shells be formed further out due to the explosion? There was no sign of arc deformations of the high redshift object or any other evidence for gravitational lensing. As a final finishing touch, I looked it up in a catalog and found the actual galaxy was a Seifert 1. It was only then I noticed the last sentence of the paper, which said, "Finally, we note the discovery of an object with Z equals 0.3799. Its alignment with one of the brightest extranuclear regions in 3C227 is remarkable." After 27 years of evidence for the physical association of such objects, I would love to know what went through the authors' minds when they decided to use, instead of the neutral term high redshift object, the term background object.
Well, that's how we treat data we don't like.
So yeah, let's I say maybe we call it, but we should read at least this first paragraph of this next chapter because it's kind of funny. I can go ahead and read it real quick.
Okay.
So yeah, quantization of redshifts. The fact that measured values of redshift do not vary continuously but come in steps, certain preferred values, is so unexpected that conventional astronomy has never been able to accept it, in spite of the overwhelming observational evidence. Their problem is simply that if redshifts measure radial components of velocities, then galaxy velocities can be pointed at any angle to us. Hence, their redshifts must be continuously disturbed. For supposed recession velocities
Distributed.
of quasars. Oh, sorry. Continuously distributed. Thank you. Thank you. Very crucial. For supposed recession velocities of quasars to measure equal steps in all directions in the sky means we are at the center of a series of explosions. This is an anti-Copernican embarrassment. So
I love that term.
Yeah, that is great. So a simple glance at the evidence discussed in this chapter shows that extragalactic redshifts in general cannot be velocities. Hence, the whole foundation of extragalactical astronomy and Big Bang theory is swept away. Should we keep going a little bit? I think we have to after
There it goes.
after that opening paragraph.
It's a big opener.
Yeah, let's go. Let's finish. Let's just finish this little page. Let's finish this page, just this page, and then we'll call it. The early history of the 72 kilometer per second redshift periodicity in galaxy redshifts is discussed in Quasars, Redshifts, and Controversies, starting on page 112. Subsequent investigations have confirmed that period and increasingly accurate redshift measures have established another even more conspicuous period of 37.5 kilometers per second. Meanwhile, the larger redshifts of the quasars have received added support for their periodicity from increased numbers of measured redshifts and also the beginning of the ability to correct certain pairs for ejection velocity components. Narrow beam surveys of field galaxies have shocked establishment astronomers by showing periodicity. The shock would have been less if they had not disregarded 20 years worth of previous observations of redshift periodicities.
That is how a scientist types out "told ya."
Yeah, right. On the theoretical front, it has become more persuasive that the particle masses determine intrinsic redshifts and that these change with cosmic age. Ooh. Therefore, episodic creation of matter will imprint redshift steps on the objects created at different epochs. In addition, it appears increasingly useful to view particle masses to be communicated by wave-like carriers in a Machian universe. Therefore, the possibility of beat frequencies, harmonics, interference, and evolution through resonance states is opened up. Pretty cool. So yeah,
Yeah, that seems heavy duty.
this book is loaded with gravy.
I can see why they had to
The guy
excommunicate this guy.
He just systematically tossed their entire model out the window.
And he was in the system too. They had to. Didn't they name? Doesn't he have like an observatory named after him or something like that? I think he does. And they had to eject him after he started getting a little too mouthy, a little too honest about what he was seeing, a little too a little too much critical thinking going on. Let's see here. What is he? He has something named after him. I'm gonna find out right now.
Dude, we read earlier that there was an extra 30 kilometers a second velocity available. Like the heliocentric model, dude. If you're trying to scoop that up, like it's right there if you guys want it. It's a quasar measurement, but you can have that one.
Funny, his Wikipedia page says he is remembered for his 1966 book Atlas of Peculiar Galaxies, which cataloged unusual-looking galaxies and presented their images. Not gonna lie, Wikipedia, that's not what I know him for. Not just for looking at unusual galaxies.
Yeah. So do we want to watch Stone's video and wrap it up?
Oh, heck yeah.
Awesome.
Oh, cool.
Incoming video from your boy.
Yeah, the soundtrack is not for children under 50.
Yeah.
But you're gonna love it.
All right, so take your young children out of the room or put some earmuffs on them.
Who doesn't love Eddie Bravo?
All right, boys. You heard the man. Earmuffs for the children.
Me and Joe Rogan were so into space documentaries, we would get high as fuck and just watch them over and over again. 8-part series, Universe. In our 30s, not as kids. In our 30s, grown-ass men obsessed. We were just we thought we knew everything about super hypernovas and neutron stars, and yeah, they're like 70 light years away, and then we were just memorizing, and then every now and then I'm watching, balls deep, high as fuck, and I'm like, I wonder why we never see real video of any of these fucking planets and stars. It's always cartoons. Whatever, they must have a good reason. So every space documentary, every single one is 100% CGI. That right there, big red flag, big red. And the one thing that got me. The one thing that got me is I always knew that the moon landings were fake. That was, and I thought NASA would, that was their job. NASA was, their job was the moon missions. And I didn't know that NASA ran all the space information. I thought it was just the moon. So I didn't trust NASA. I'm like, they faked the moon missions. I can't trust them. But I thought surely there's another agency that's in charge of all the different planets and balls deep into space and all that shit. Like, I remember on Joe's podcast, Joe would say, dude, there's people that even believe the earth is flat. And I'm like, what? What are they, Amish or something? How retarded can they? Like, I thought they were so dumb. And then another one of my students brought it up. Another one said, hey, you ever look into flat earth? I'm like, dude, you just fuck. Like, I don't ever want to talk to you again. And then he's all like, listen, I got a master's degree in engineering. You should look into it. I'm like, oh my God. I felt like I can't talk to this guy no more. As soon as you say flat earth, I'm like, dude, you are retarded. So then I go online. I go, I'm just going to send him as many fucking pictures of earth from space. There's got to be fucking thousands of them with all different shading and the sun over here, the moon over. There's got to be all sorts of amazing pictures of earth from space. And as soon as I got on, I'm like, let's see, what is it? And I started looking at them. These are all cartoon. And then I went to the source of the pictures and they were all like, NASA.gov. I go, wait, right there. That's all I needed. I'm like, wait a minute. NASA is fucking controlling all these pictures of Earth from space? Right there. I'm like, there's a problem.
Nice.
Awesome video.
Yeah.
It's one of those videos where you got to turn the audio down and just watch the video, and then turn the audio up and just listen to the audio to get the full effect, because there's so much going on there.
Agreed, but the content there is pretty good. The trick they played is pretty sneaky.
Yeah, this is the absolute magnitude scam right here. And the entire scale that you're looking at, the magnitude scale, is retarded. You can see that as you go to the left on the scale, it's 2.5 times brighter every tick mark to the left. Does that make any sense at all? No.
Has anyone ever tried, have you ever like brought this up to a Glober and gotten a response?
Sending it to Parks now.
Nice.
We demand immediate answer. Nah, he's pretty chill. I sent him some of that stuff from the Tycho lads, and he read it and got back to me on it. So we'll see what he says about this.
Massive props. Shout out Parks.
Yeah, dude, shout out to your boy.
Cool. So go ahead, Ken.
Just so I think I understand what I'm looking at here, absolute versus apparent. When we say apparent, that means what we see, right?
You got it. And absolute is what they're trying to tell you how bright it is. Absolutely. Like if you're right next to the star, how bright it is.
Oh, so it's a magic trick.
It's retarded.
Exactly. It's all bullshit.
This is what you see, but this is really what it is, right? Isn't that what that is?
That's what they're trying to say. Yeah, they're trying to say, oh, you see that it's 4.1, but it's, or actually you see that it's 0, but it's actually 4.1. And that other one that looks like 0, it's actually negative 10.47, 380,000 times brighter than the 0 value. You know what I mean? Like, get the fuck out of town.
I thought so. I was
And are they trying to use that?
It can't be that simple.
This is the widely used magnitude scale since day one in astronomy. This is it right here, guys.
So you're saying if I was
the perpetration.
But are they trying to do that? Is it to justify the distances from the stars?
It's part of it.
Well, it's not doing. It didn't go too well with parallax, right? So they needed something else.
Are you
and they
saying
just
that
made tons of assumptions about distance using this shit here.
those X-rays wouldn't obliterate me at 381,000 times the strength, which I see it right now. If I was standing next to it, would I not be just obliterated by that ridiculous luminosity? Be like, come on. That's a hell of a candle. All right. Anyway.
Dude, it takes a really bright
Yeah, no,
candle to map out the cosmos.
It's just ridiculous, man. You might even play it again because there's a lot of detail here, especially the math.
No, that's an awesome breakdown. This is what you see, but this is what we've defined it as, so we can base our distances and our whole cosmology off of it. Thanks.
Yeah,
And here's a nice here's a nice ruler for you to reference how we interpret it for you, the thing that you can't see, but we all have agreed upon this absolute value. So, you know, if you dude, that's what have they done to us, Stone?
Like, good luck fighting that. Yeah, we already figured that out.
It's mental genocide.
Dude, they punked us so hard.
Right after we read all that redshift stuff.
They got lensing in the opposite direction of what it should be predicted at. They got stars that have completely different magnitudes than what any man has ever observed it with their oculars.
But just must be so because is lensing and redshifting such.
Yeah.
Never mind the fact that the distances between them and the the redshift values are totally different, even though they're right next to each other. Pretty cool.
Dude,
Don't worry,
one coming
it's
from
all
the other.
expanding, and it's just relative to the expansion.
It's just rippling backwards in time. Yeah. All right, dude. Well, I think that about wraps
Well,
it
there
up.
you go. That about wraps it up, indeed. Thanks everyone for tuning in. You may catch some of us tomorrow for Flat Earth Fridays on X Twitter Spaces. Also, of course, as always, check us out next Tuesday for Ether Roundtable number 33, and then reading night again next Thursday night. We'll probably we already have another Twitter space on the books. Is that right for Monday?
Who's presenting Tuesday? What are we doing?
Yeah.
By the way.
Okay. So Monday's Twitter space is going to be like a meta workshop. So we're going to take some of our presentations that we've done recently that are, you know, dense material. We'll have it broken down into like 5 fine points that can be, you know, articulated and used in arguments and stuff. So we're going to go over like how that'll work and what the arguments are supposed to represent and what they're refuting, etc. So it'll be a nice little like 3 little mini presentations by each of us. So I'm going to do relativity and absolute space. I think Toby, I'm wanting him to do the geodynamo model because I think that's an excellent argument against the globe and its ability to make a magnetic field. And Shane, like whatever you want to do, but I'm hoping like Sky Miles map related or something.
Yeah, we'll do maps. We'll do a quick cartographic cosmograph lesson in 5 minutes to show everyone what we're dealing with.
Nice. Well, you can take as much time as you need. I'm just, you know, general outline.
Cool.
Can I add one more thing?
Absolutely.
Do you want to present?
I think it would be cool. Well, no, I'm talking about another thing. Like tomorrow night is Flat Earth Fridays, of course, starting at 9 Eastern.
Yep.
How about we do another repeat like we did last week, 8 Eastern, here. And I will release my new video, a couple of thoughts about Google Earth.
Yes.
That sound fun?
Yes.
Yeah, that sounds awesome.
Yeah, it's totally reworked and far more coherent now.
Cool. So
Awesome.
8 p.m. here tomorrow night. You heard it live on the spot announced. We're going to check out Stone's new video about Google Earth and some thoughts about that and some implications of the global coordinate system as I understand it.
Be there or be rhomboid.
That's right. All right, everyone. Take care and thanks again for being here and